Let's get started. Now here I have a Jupyter notebook and I have connected to my local instance of my GPU. So let me just open up a new terminal and show you what we're working with now. So if I do NVIDIA SMI, so we have a GPU which is 136 MB being utilized and has about 24 GB of VRAM. All right, so this is a 4090, a consumer grade 4090. So just to get us started. Now, as I code down, I'm going to be coding because it makes sense to code, and you guys can feel free to watch it, skip around, and whatever works for you, right? So yeah, let's get started. So import. So what we're going to do now is load the necessary data set, which is basically a dummy value of sorts. So here is where I was saying you figure out the data set and kind of go from there, right? So we can use the dataset class provided by Hugging Face. So we can do import numpy as np, and from datasets import the class dataset. All right, now you know what, I'm going to close this off because for this session, yes. All right, so that was my Grammarly doing its thing there. Anyway, so from dataset now, let's set the sequence length and the dataset size to 512. And then let's create a dummy data set. And then input IDs. So this is the structure that we need to follow in order to set, in order to use the dataset class. So I'll be showing you. So random MP. So we're just creating a random dataset, rand int of dataset size, and sequence length. And then we have labels, which is again np.random rand int from 0 to 1 in the dataset size shape. All right, so now we have the dummy dataset set, and then we can say ds is equal to the dataset class, and then pass in the dummy dot from, it's a dictionary type, right? So from dict, and then pass in this dummy data. And then this is, it depends. So if you're using PyTorch, you can say set format and then set pt. So this will just make everything in the PyTorch format. All right, now that we have the data set, now if we quickly take a look at ds, so it has features and number of rows. So input IDs and labels. Yeah, so this is the input IDs. And if we take a look at the labels, their corresponding labels. Yeah, cool. So now that we have that covered, now what we're going to be doing is we're going to be using another Python library called pynvml. So from pynvml, so this is NVIDIA management library imported to Python. So if you've ever used like I just showed you, the NVIDIA SMI, right? You can just do this instead of doing NVIDIA SMI on a terminal. You can use Python to do that. So that is what the use of pynvml is. So import all the. All right. So def. We're just going to create a helper function here. So that code I'm just going to copy paste it and just quickly walk you through it. Okay, so what we're doing is we're going to print GPU utilization as to how much the GPU is being utilized based on the operations that got performed. So if we say GPU utilization, that does nvml init, which is a function coming from py-nvml, handle the device get handle index. So we're getting the zeroth device, which is basically the first GPU. If you have like 3-4 GPUs, you can pass in a list, right? And then info get device memory info of that handle, and then print the GPU memory which is occupied. All right, and then we do print summary, which takes in basically a result, right? And then it gives the metrics, that has metrics and train samples per second. So don't worry too much about it. So this result is basically the output of the model that got trained, which will become clear just in a moment. All right. So now if we do print GPU utilization and call the function, so GPU memory occupied is 505. So far so good, right? So we've used about 505 megabytes, which is fine. I think this is to run the operating system and the kernel and whatnot. So that is being used for that. So 500 MB is what we need to run the basic system itself. Okay, now what I want to show you is, let's load a tiny tensor, right? So let's load a tensor into the GPU. So I'm gonna do import torch, and then torch dot ones. So it's a 1x1 dimension, and then I'm going to do dot two CUDA. So this is where you set the device basically, and 2 CUDA means it is going to push it to the GPU. And then now if we do print GPU utilization, let's see. Oops. Yeah, you see that just to load a tensor of 1x1 dimension, it took about 400 MB again. So you see that, right? So we have to be able to optimize all of these. So now let's get down to business, if you will, right? Let me just make some space so that I have enough space, and you can see my face and the code as well. Is this minimized? Yeah, okay. Now let's load a transformer model. So from transformers, import auto model for sequence, auto model for, you could use whatever model you want, sequence classification. All right, so let's just load that up, and say model equal to auto model for sequence classification, and then from pre-trained. So this is going to download the model for us. And what model? I'm just going to copy paste that model name. BERT. So we're going to use a BERT and dot two CUDA. Then you can say print GPU utilization. So it's gonna, now if you did not say dot two CUDA, it was going to load it on CPU, which is not what we are looking for. So 2247. So 2247 MB of VRAM is being utilized. Now I'm going to copy some default hyperparameters or arguments, if you will, for the model, so that we don't have to pass it every time. So output directory, I'm going to set it to temporary. Evaluation strategy based on the steps. Number of train epochs, let's just do 1, because in the best interest of time, we don't want to be here sitting training all day long just to see the metrics, right? Log level is the error report to, we don't want it to report to, you could report it to weights and biases, right? You could report it to tensor board and so many other things, right? So we just keep everything small, nice, and simple. Okay, so these are the default args. Now let's do just the basic vanilla training, right? Okay, so from transformers import training arguments, the trainer itself, the trainer class, which is essential, and the logging. And then we'll set the logging to set verbosity error. Okay, so training args training arguments, and here we will pass the per device the train batch to, let's say, 4, and then destruct the default args, and then set the trainer equal to trainer. The trainer takes in, if you will, it takes in the model equal to model. Its named arguments args is the training args, and the train data set is coming from the data set. Now we have to put this to training mode. Now this is where the result is coming from. Result equal to trainer dot train. Should get into training mode, and then print summary of results. Okay, now we just have to sit and wait for this to train. All right, so we can see that the training time took about 20 seconds, right? And it did 25.32 samples per second. And you see the GPU memory is about 12 GB is being used. 12 GB is being used. Already you can see that just training a vanilla BERT model with very basic, with a batch size of 4, and not a lot of things are going on. This is as vanilla as it can get. And you can see the GPU is being used. The memory footprint here, so to speak, is about 12 GB. Now you can see how quickly this is going to get populated. And if you were to use a batch size higher, then obviously it's going to get more and more. So this is where the real problem starts, right? Now let's see how we can tackle them. So the first thing is called as gradient accumulation. So this is the key part. So I'm going to put this mark down and say gradient accumulation. Yes. And what is gradient accumulation? Now when we set a batch size, let's say now here we set a batch size of 4, what happens is the gradient for the entire batch gets calculated. And this is where most of the training time is gone, right? To calculate the gradient for the entire batch. And since we are calculating for the entire batch, it's going to take up a lot more space. But what we can do is we can do something called as gradient accumulation, where we start accumulating the gradients by slicing these batches, right? So instead of taking the gradient for the entire batch of 4, we're going to break the batch sizes, right? And then calculate the gradient, start accumulating them based on the gradient accumulation step parameter. So let's see how we can do that. Now all we have to do is, I'm going to copy this code because it's pretty much the same code and few things are going to be changing. So per device batch size, we're going to set that to 4. Okay. Or for the sake of example, let me set it to 1. And then here I can say gradient accumulation steps is 4. So what effectively is happening now is we are passing a batch size of 1 and asking the gradients to get accumulated after every 4 steps, right? So effectively this turns out that we are basically passing in a batch size of 4. So for instance, if you wanted to pass in a batch size of 64, what you can do is if you wanted a batch size of 64, you can pass in the batch size here, per device train batch size to 4. You can set that as 4, and then accumulate gradients after every 16 steps. So 16 times 4 is 64, if I'm right. Yeah, so it is 64, right? So this effectively gives, it tries to mimic the batch size of 64. But for now, let's keep it simple. Let's keep this to 4 and this to 1, and everything else pretty much stays the same. So now let's see the output metrics. All right, now we can see that the time is about 23 seconds. Samples per second is 21.5 samples per second. And GPU memory occupied is pretty much the same thing. Now, what the actual beauty is, let me show you, is instead of 1, I'm going to set it to 4 and set the gradient accumulation steps to 4. So effectively, it's like a batch size of 16. So now we'll see for 1 and 4, it kind of like was surfacing around the same size, but now we've increased the batch size, and let's see. Yeah, you see that. So the time was reduced. So we're using a batch size of 4, and we're accumulating the gradients at every 4 steps after the forward and backward, right? And you see the time taken was still less, and the samples per second was more, and the memory that's being used is not too much when you take into consideration that we are doing a batch size of 16. All right, so if you see, now that we've used gradient accumulation with a batch size of 1, and for every 4 steps, we see that the GPU is being utilized even lesser. So there's one nice technique that you can release the cache. So you could do torch.cuda.empty cache, and then let's see if it made any print GPU utilization. Yeah, you see that the cache, whatever the cache the model was using, the CUDA cache has been emptied, and we have more space to play around with. So this is one nice technique to remember, because now we're going to be doing a whole lot more. So we're going to be consuming a lot of GPU memory. That's why I wanted to show you this nice technique to release some cache if there are any. All right. So now that we have understood what gradient accumulation is, just to reiterate, gradient accumulation is basically when, now instead of calculating the gradient on the entire batch of, let's say 4, if we give 4, instead of calculating on the entire batch, what it will do is it will break it down. It will break it down for every forward and the backward pass, calculate the gradient or accumulate the gradient after every 4 steps of the batch sizes, and then once that is done, it'll start accumulating the gradient so that it becomes faster. And you can also see the time taken is also, so obviously 3 seconds more, but you've reduced a lot of GPU usage. From 12 GB, we've come down to 7 GB, right? So that is what I wanted to show you. So this is effectively like getting a batch size of 4. So if we wanted 64, like I said, we can set the gradient accumulation step to 16 and have the batch size, per device train batch size to 4. All right. Now moving on, let's see how we can save a bit more. So moving on, we're going to do something which is even better, which is called as gradient checkpointing. This gradient checkpointing. So let's quickly read this out. Even when we set the batch size to 1 and use the gradient accumulation, we can still run out of memory when working with large models. Okay. So in order to compute the gradients during the backward pass, all the activations from the forward passes are normally saved. So what it is saying is, so even if we were to use gradient accumulation and set the batch size to 1 and accumulate gradient after every 4 steps, even if we do that, sometimes we can still run out of the memory depending on the GPU you're working with. So this is already using 4 GB. So if you were to have a 1050 Ti or something like that, right, we already know that we have exceeded the capacity. It's only 4 GB. So if we still use gradient accumulation, we can still run out of CUDA, the GPU memory, right? So what happens is, in order to compute the gradients, what the framework does is, it in order to compute the gradients during the backward pass, all the activations from the forward pass are normally saved. So all the activations that we get from the forward, so when we do model.predict, which is basically a forward pass, and we're going to have an activation, right, at the, let's say, the last layer. So when we do the forward pass, all the activations are normally saved. But this can create a big memory overhead, obviously, if we were to save all the activations from the network, right? It can obviously create a memory overhead. Alternatively, one could forget all the activations during the forward pass and recompute them on demand during the backward pass. Well, this seems like a good way to escape the memory overhead, but then this comes with the cost of compute overhead, right? So significant computational overhead and and if there is more computing required, it will slow down training, obviously. So gradient checkpointing is where it strikes a compromise between these two approaches and saves strategically the selected activations throughout the computational graph. So only a fraction of activations need to be recomputed for the gradient. So what gradient checkpointing does is, now instead of, okay, so what were the two possible options? One was to the normal way is to compute the forward pass activations and then store them, and then when we're doing a backward pass, use these activations, right? But this comes with a memory overhead, so it uses a lot of GPU memory. Alternatively, what we could do is we can forget all the activations that got calculated, and when we need them during the backward pass, recalculate them. But again, now if we are eliminating the memory overhead, we are introducing the computational overhead, because we have to recalculate all the activations from the forward pass again to calculate in the backward pass. So this will again slow down training. But what will gradient checkpointing do is that it kind of tries to strike a compromise between these two approaches, where only the necessary activations it'll keep in the memory, which it deems as important, will keep in the memory, but the other ones it will take it off. So again, let me read it out. Gradient checkpointing strikes a compromise between the two approaches and saves strategically selected activations throughout the computational graphs. So only a fraction of the activations need to be recomputed. So we see that gradient checkpointing is kind of like the best of the both worlds, where it does not store all the activations from the forward pass, but at the same time, it will maintain, or it will store the key activations that it thinks or that it deems important, and recalculates the activations to compute the gradients. So this is where the gradient checkpointing comes into picture, and we'll see how it will kind of save even more. So let me just copy this line of code. And we can use gradient checkpoint in conjunction with gradient accumulation. So that's a good thing. So what we can do is we can set gradient checkpointing flag to true, and then pretty much everything else stays the same. Now that everything else stays the same, we can just print it out and see the metrics. 97% of the GPU is being utilized and about 8 GB is being used. Yeah. 8592, 8961, all right. And you see, it took about 31 seconds, but we ended up saving a lot more, right? Now, this is 8 GB because of the fact that there is already this model in the GPU memory. Now, if I were to clear everything, let me just clear the kernel out or restart the kernel, right? And then show you guys how much it is actually using. So that is actually the fair way to see it. So let me do this and run it. So for now, it's only, once we loaded the CUDA, all right, put it to this thing and get the default args. So here, what I will do is I will not train them. I'll just initialize the variables, and I'll also not do the gradient accumulation. I'll do the gradient checkpointing along with gradient accumulation. So this will give the true results, so to speak. because obviously we'll not be doing every time, right? We won't be building a model which will do first gradient accumulation and then gradient checkpointing. So that is not the fair way to see it. But yeah, you see that, although it takes a bit more time because obviously it needs to recalculate the forward activations. uh, so that is kind of the trade-off. And samples per second is again lesser. Higher the better, of course. But you see that the memory usage from 7 GB, almost 7.9, 7.93, okay, 7923 MB, it has come down to 6411 MB, right? So that is a significant memory footprint that is being saved while doing pretty much the same thing, right? All we added was setting the gradient checkpointing to true. And you see the power of the train argument class. All we are doing is we're not adding too much code changes, but here we're literally just adding few parameters of the class, and we are achieving what we want. And I think this is the best or the easiest way to do this. And thank you for Hugging Face for building such a powerful framework, right? Now, are we done? No, we're not still done. There are a few more things that we can optimize for. What we can do is we can do another thing called as FP16 training. FP16 training. Let me just okay, so FP16. So what this is floating point 16 precision. So what we can do is we can set the training in the training arguments. We can set this variable FP16 to true, and what it will do is instead of training the model on the torch D type of float 32, it will quantize it or minimize the dimension to FP16 and save some memory there, right? But obviously, if we are trying to reduce the dimensions, we are losing some information, right? So from FP32 to FP16, we're definitely losing some information, but we're making up by the fact that we are training quicker and we're using less memory. So that's kind of the trade-off. So let's see how we can do it. So let me just copy the same code and paste it. And all we do is set FP16 to true. Everything else stays the same. So I'm going to set the... Also, I'm going to add gradient accumulation steps after every 4 just to keep everything intact, and gradient checkpointing to true. All right. Now the fair way to look at this again is to read on the kernel, but I'm not going to do it. But if you wanted to see the differences, I think that's the fair way to do it. Restart the kernel, set up all the variables, and then just use the FP16 directly. I'm going to share this collab in the GitHub repository, so feel free to. And also I'm going to add the documentation from the Hugging Face itself. Okay, so you see that if we do FP16 for pretty much the same thing, it took 21 seconds and 24 samples, but it is 9489. But this is not actually the true memory usage. But you know what? Let me just restart the kernel and run everything again, just so we are doing a fair comparison and not just okay, and then come back to FP16. So this will typically train quicker because we are using less precision, and it uses less memory because of the fact that, again, we are using less precision. So let's see the results. Yeah, you see, it took about 21 seconds. Here it took about 31 seconds, and it is doing 24 samples per second. But you see the GPU usage is 6913, and compared to this just gradient checkpointing, which was about 79 something. Sorry, gradient accumulation was about 79 something. Gradient checkpointing 6411. But again, we gave up in the time here. Obviously, we're just doing one epoch, and the time was almost 10 seconds more, almost, right? So we can see that that's a trade-off. And even samples per second, obviously, since the time is increased, it cannot do more samples per second because it has to recalculate the forward activations. But in FP16, all we are doing is we are not playing around with anything else. But of course, we are setting the gradient checkpointing to true, gradient accumulation also. We're using all of this together, and we're still achieving good time and good samples per second with, I think, really good memory occupied if we compare it to just the gradient accumulation alone or even gradient checkpointing. Now that we have these out of the way, so what was the first one? I mean, we just basically loaded the vanilla, did the training, then we did gradient accumulation, then we did gradient checkpointing, and then we did FP16 training. So, are we done? No, definitely not. What we can do is we can do a bit more optimization in terms of the optimizers itself. So what Adam does is Adam is known to converge quicker and has good accuracy in terms of the activations. But what we can do is we can use something called as add a factor, ADAFACTOR. Adam or the Adam W. Let me just copy paste that here. Yeah, so let's see here. So the most common optimizer used to train the transformer model or pretty much anything nowadays is the Adam or Adam W with Adam with weight decay. So this is the most common optimizer. So Adam achieves good convergence by storing the rolling average of the previous gradients. So what it does is it tries to maintain an average or like a table that keeps the average of the previous gradients. So however, adds an additional memory footprint again. So every time we try to save something after it being computed, we are adding it to the memory footprint, right? So that becomes a memory overhead in order to of the order of the number of model parameters, right? Fine. Now, one remedy to this is to use an alternative optimizer such as add a factor. So what add a factor does, so let me just copy paste that. So what add a factor does is instead of keeping a rolling average for each element, add a factor only stores the aggregated information. So it does not like have a lookup table or of sorts where it keeps the average of each gradients, right, after each computation of the gradients. It just maintains a weight matrix. It just only stores the aggregated information. So it does not do a rolling gradient computation. What it does is instead it only stores the aggregated information, right? So basically, row and column wise sums of the rolling averages. That's all. So again, now obviously, if you're not storing a lot of computed information, we're going to reduce the memory footprint considerably. But one downside is that it does not really converge well. So do keep in mind, using add a factor, yeah, you can reduce the memory footprint, but it does not converge well. So let me just copy the code to show you guys. Now here we say optim is add a factor. And obviously we can set the gradient accumulation steps to 4 and gradient checkpointing to true, and even probably do FP16. Where is that? FP16 to true, and so this to 1. Yeah. Now let's check it out. But again, so keep in mind, every time we run this progressively, it's not the accurate way to measure the GPU memory used. What you should be doing is run this the first time and see how much the memory is being used. So that is the fair way to do it. Yeah, you see that. So it is about 7307, and it took 22 seconds, 23 samples per second, which is good. But again, the convergence is not really that great in typical scenarios. So that's why we don't prefer using add a factor, although it reduces the memory footprint, because we need the models to be accurate as well. So what we can do is, now obviously since add a factor is not good, we can use another optimization technique called as 8-bit Adam. So what that does is, instead of doing the Adam on the 16-bit or probably even 32-bit, if you don't set the FP16 to true, you could use 8-bit Adam, where you can quantize even more from 16 to 8-bit floating precisions, and then calculate the gradients and do the optimization based on that. So now let's see how we can implement that. Okay, so let's quickly take a look at the implementation of 8-bit Atom. So for this, we need what is it called? Bits and bytes. So I already have it installed, so that's not a problem. So you need bits and bytes installed, where we can use that to implement it. Import bits and bytes as B and B from torch. Import the NN module, and then from transformers, so that is PyTorch utils, import get parameter names. Okay, as okay, now training args equal to training arguments, and then the per device, we set that to 4, and then the destruct the default args. Now we say dk params. Dk parameters is get parameter names of the model, right? And then as a list, we pass in the nn dot layer norm. Then dk params equal to for name in dk params, give me the name if bias not in name. So what this is doing is give me the name for in dk params if there is no bias, if there is no variable, or if there is no this string bias in name. So that will become clear in a moment. And then optimizer. So this is just the basic syntax that we need to follow. Optimizer OUPD grouped params equal to its list of dictionary ms params for comma p in model dot named arguments or named parameters. Give me n. Oops, sorry. Give me p if n in dk params, and then weight dk is, let me give a space between here, is training args, this one, the weight dk. Params so again for n comma p in model dot named parameters if n not in dk parameters, give me p, right? And then again the weight dk zero, or you could use the training of weight dk. So that sums up the parameter group optimizers. Now optimizer, all right, now that is done, we can copy paste this code. So all we do is we set up the DK params and pass it to BNB optimizer Atom 8-bit. That is coming from the bits and bytes framework. So we are setting the parameters and weight DK 2 times. But yeah, these are the optimizer group params. You can, if you want to learn more, you can check out the documentation. But yeah, this is pretty much it. So here you can see that we have used the trainer and yeah, set the trains. So it took about 20 seconds, 24 samples per second, and 7.23 MB is all being used when we've used 8-bit Atom optimizers. So you can see that, just to quickly reiterate, we have gradient accumulation, gradient checkpointing, FP16, add a factor, which is just so that you know it, just to try it out. But then it'll be best advised to use 8-bit Atom whenever possible to train the model. Now what we can do is we can add everything that we have learned till now, that is the batch size, the gradient accumulation, gradient checkpointing, FP16, and also adding the 8-bit Atom. So let's see what happens. Meanwhile, let me show you the bits and bytes. Yeah. Bits and bytes documentation. So this is the package itself. What you can do is, instead of using the Atom optimizer, you can just put BNB Atom 8-bit. Arguments stay the same. Whatever arguments you're passing to Atom, it's pretty much the same. And you could also change the NN embedding to BNB embedding. So yeah, that is pretty much it. So that is as simple as it gets, is all I'm trying to say. We could use that package, and then if you get into bits and bytes, we have the Optum Atom, we have the 32-bit, and we have the 8-bit, and all of these pretty much stay the same. And whatever we coded out here in the notebook, so whatever we coded out, we were just coding out the parameters, weight decay. That's all we did. So if you get back to the documentation, you see that params, the learning rate, the beta, the weight decay, the epsilon, the weight decay, all of them. So that is what we were trying to just code it out. Although it might seem a little confusing and tricky, it's not really. You could choose to opt out of all those extra things that we coded out and keep the normal just 8-bit Atom going on. So what you could do is, now instead of saying this, what you can do is you can do this. Now instead of doing all of those, what you could do is you can say this, Atom 8-bit, do ADAM 8-bit. And of course we need the params. So that is the necessary argument. We can pass in the params. That's it. And then what you can do is you can copy this code, paste it in here, and then set this to Atom 8-bit. And it should be fine as well. So you don't have to really do all of this. But however, since we have set our own values, you can change around, play around with it. But a necessary argument is the optimizer group names, where you get the params and the weight decay, params and the weight decay. So yeah, that's pretty much it. That's why you can go through the documentation. It becomes even more clear and concise for you. So this pretty much sums up this video. In the next video, we'll be taking a look at something called as the Hugging Face accelerate, where we can use that to scale our training. So let's say if you had multi GPUs and you want to train on multi GPUs, you could use accelerate. The scaling becomes easier, and it just does a lot of other things to help us out and help the developer, so that the training and all the housekeeping of the model itself, of the GPUs and things of that nature, becomes easier. So we don't have to waste our time trying to optimize for those. So accelerate is again a good library from Hugging Face. And the beauty about accelerate is we can use the same trainer, the same training arguments that we used here. So pretty much it stays the same. So in the next video, I'll be showing you how to use those the accelerate. And also keep in mind that there is this amazing new paper that has come out called as QLoRa, which says making LLMs even more accessible with bits and bytes and 4-bit quantization with and QLORA. So LORA stands for low rank adapters. So I'll be talking about that paper along with how we can use few aspects or already implement few aspects of that paper. And also there's another thing called as PEFT. Yeah, which is parameter efficient fine tuning, the state of the art parameter efficient fine tuning. So, what we can do in this is we can fine tune a large language model using PEFT, and all the things that we will learn from the paper, the QLoRa, which I said, the quantized low rank adapters, and how we can implement from of that paper the elements of those papers. They do 4-bit normal float. They come up with a new architecture, or not an architecture, a new data type called as 4-bit normal float, N4F, normal float 4-bit, to implement a few aspects. Obviously we're not training on that, but we're doing inferencing and few other aspects on the 4-bit normal float, and also using FP16 double quantization as well. So all of those things, if we have that in our arsenal, it's a good tool, set of tools and skills to have, so that you are really you're really optimizing your training pipeline. And the model training, or even fine tuning your own model, LLM model should be as easy as it can get. But yes, that is pretty much for this in this video. So if you really found some value in this video, do give it a thumbs up, like, share and subscribe. And if you have any queries, doubts, feel free to leave them in the comment section below. I will definitely add um, all the necessary resources, the documentations, and whatnot in the description below. So until then, stay in the loop. Thank you for watching. Yeah, take care.